Hi everyone. I would like to present about water and fat separation in magnetic resonance imaging using Dixon technique. Firstly, why this is important. Magnetic resonance images that are obtained in vivo usually contain signals from both water and fat. However, the fat signal tends to overpower the signal from other tissues. In many pulse sequences, the fat appears hypertense, and that could cause image degradation. For example, it's difficult to spot important anatomical features like cancerous lesions. On the other hand, separated fat signal can be used for some clinical applications related to obesity, diabetes, fatty liver diseases. Another example is the diagnosis of bone marrow diseases. So how can we do this? How can we suppress or separate fat signals? Actually, we can use the property of chemical shift between water and fat. From this graph, we can see that there is a chemical shift between water and fat, which is 3.5 ppm. Or 450 Hz at 3 teslas. That means fat and water have different resonance frequencies. They precess in the transverse plane at different rates. Dixon technique is one of the approaches that utilize this property to separate fat and water. Some fat separation techniques use the chemical shift property as well, like selective saturation and selective excitation. In selective saturation, first excite and saturate the fat magnetization before water is excited for imaging. However, in selective excitation pulses, we simply excite water magnetization and leave fat magnetization alone. But these two approaches are sensitive to field inhomogeneity. Before discussing how Dixon technique is used to solve the issue of field inhomogeneity, I want to explain about the signal model that we will be dealing with. Firstly, a fundamental assumption of Dixon technique is that water and fat are the only two signals contributing to chemical species in the object to be imaged. So in this equation we can see that we only have the water and fat signals, and the phase between alpha is the phase between water and fat, phi is the phase error because of the field inhomogeneity, and P0 is the phase error due to other system imperfections. We can see that water, fat, P and P0 are position dependent, but for simplicity we can drop these and the equation will look like this. And this is the vector representation of the system that we are imaging. It consists of fat and water, and alpha is the phase difference between them. It is important to note that alpha is chemical shift dependent and also echo time, and also B0, and phi is field inhomogeneity dependent and also echo time as well. Firstly, I would like to explain about the general idea of the Dixon technique. Actually, we get two images, one in phase image with a 0 phase difference and another one with 180 phase difference. The summation of these two gives water signal, and the subtraction of these two gives fat only image. This is a vector representation illustrating this idea. If you can see the sum, if we sum the vectors, we get water, and the subtraction gives fat. A more accurate representation is these two equations. This is the in-phase signal, and this is the out-phase signal, 180 phase difference. If we assume that phi is 0, a simple summation and subtraction gives water and fat as these equations. However, when phi is not 0, these two equations don't provide clean water and fat separation, and the water-only image and fat-only image will generally contain mixture of both water and fat. As a result, the success of the two-point method is affected by this phi value. If it is not 0, which means that the field is inhomogeneous. So, to solve this problem, we can use the 3-point Dixon technique. In the 3-point Dixon technique, we don't take only 2 images, we take 3. We take the third one, for example, at 360 degrees phase difference. And we can utilize this third image to get the V value. If we get the V value, that means we solve the problem of the B0 inhomogeneity. So this equation is used to solve this problem. And after computing the B0 inhomogeneity, fat and water signal are computed through linear equation resolving. And at the end we get these two equations. This is for water and this is for fat. Again, we can see that it's again a summation and subtraction of in phase and out phase signals, and K is just a sign factor. So how can we get these images? We can use the normal gradient equal and also spin equal to get images with 0 phase difference, 180 phase difference, or any phase difference. We can utilize this equation, the alpha equation, to find the phase difference. For example, this is the in phase signal, and to get an out phase signal we can manipulate delta value. For example, when the delta value is 0, we get a 0 phase difference. When the delta value is 1 over 2f, we get a 180, this one, a 180 phase difference, and so on. I would like to conclude by showing some images acquired by using this technique. For example, this is a liver images using Dixon technique. This is an in-phase image. This is an out-phase image, 180 phase difference. This is the water-only image, and this is fat-only image. From this image we can see there is two lesions, and we can see the difference between this one and the in-phase image, and this is quite good compared with this one. Another thing, we can see much in the fat image in this case. However, fat image can be very useful in other cases, especially in bone imaging. For example, in these two images we can see the fat signal is quite good, and fat signal is good when imaging bone because bone doesn't have much water. And this is another image. We can see that we can use water image to see the muscles, joint fluid, and we can use the fat image to see dermal fat, bone marrow, and other things. And thank you very much for paying attention.